Hi there, welcome to this new video of optimization methods. In this video we'll have a look at the exam of June 2024. As usual, we'll only have a look at the exercise questions. For the theory you have to refer to the theoretical course. Well, let us start directly with questions 1 and 4. For question 1, well, you have to find all the local extrema and saddle points of the function that you see on the screen. That is f of x, y, which is sine of x times cosine of y. And then in question 4, you have to apply Newton's descent method to this same function and perform the first iteration with a step size 1, starting from the initial point x0, y0. So you have to obtain this first iterate x1, y1. I suggest that you try to do this by yourself if you're preparing your exam. Well, let us now have a look at the solution. For question 1, well, the idea is of course to first compute the gradient, right, and then to compute the Hessian. The solutions are given over here. So first we have to find the critical points. These are the points that make the gradient 0. So in here what you could do is make sure that the cosine x is 0, and then in the next element you have to ensure that the sine of y is 0. Another way of making sure that the gradient is 0 is to impose, for instance, that cosine y is 0. This is what you see over here. And then in the second element you have to impose x such that sine of x is 0. So you have critical points of two types. Here's the first type and here is the second type. Of course you work with trigonometric functions, so there are more than one x and y that make sure that cosine x is 0 and sine y is 0, right? So for instance, for x you have pi over 2, but you have 3 pi over 2, 5 pi over 2, minus pi over 2. So one way to write this is as follows. And of course you have something similar for the sine. So you have a whole bunch of critical points, and you can do something similar for the critical points of type 2. Here are the solutions. Let us go back to the critical points of type 1. Now we have to kind of evaluate the Hessian. You see here that these elements will be 0. This is what you see over here, right? And now we have to have a look at these elements. Notice that this element is equal to this element here. So what we have to do is evaluate this quantity here in the critical points. It's kind of easy to see that, for instance, if K1 is even and K2 is even, well, then both the sine and the cosine are just 1. So this thing over here will be minus 1. You can do similar things for the other cases here. K1 uneven, even, so you have a 1 over here. K1 even, K2 uneven, you have a 1 over here. And for the situation where K1 is uneven and K2 even, you'll have also a minus 1. So you have two situations. You can have minus 1. This is in this situation, or you can have a 1. This is in these two situations, right? So in situations A and D, we have a Hessian that is as follows. Well, these are the two eigenvalues here. So you see that they are both negative. So we know from the course of linear algebra that H is negative definite, and we have maxima in these points, right? In these situations B and C, we have a Hessian. That is simply the identity matrix, and of course that's a positive definite matrix, and we have minima in these points, right? So now let us have a look at the situation where we have critical points of type 2. What we have done is zeros over here and zeros over here. This is what you see over here, and you see that you have the same quantity in these points over here, right? So what you can do is compute the trace. Obviously it's 0. Remember that the trace is the sum of the eigenvalues, and then you can compute also the determinant, right? And of course, since you have the same quantity over here, the determinant will be negative. So the product of the eigenvalues will be negative. So this means that you have a positive eigenvalue and a negative eigenvalue. So H is non-definite, right? And then you have, of course, a situation where you have a saddle point. Well, let us have a look if we can check this with MATLAB. In MATLAB, what you can do is make a surface plot, right? And then we can have a look at the critical points. Remember, we had critical points of type 1 and 2. Here are the critical points of type 1, right? And then we can have a look at the situations that correspond to maximum, right? These are these ones, and there we'll put a red dot. At situations where we have a minimum, we'll have a magenta dot, right? And then we'll do something similar for the critical points of type 2. Here they are, and we know that they should be saddle points, right? And then these points will mark with a white dot. We can run this code and see what happens, and this is what you obtain. You see indeed that the red dots are maxima, the magenta dots are of course the minima, and you see clearly that the white points are, well, saddle points. So let us have a look at question 4. Here we have to apply Newton's descent method on the function that we've considered before, starting from this initial point over here. Newton's descent method uses the curvature of the function f, so we need the Hessian, right? So the first thing that we have to do is to evaluate both the gradient and the Hessian at the initial point, right? So this involves a few calculations, right? But if you know that sine pi of 4 is equal to the cosine pi over 4, which is square root of 2 over 2, and that the sine of pi over 6 is a half, and the cosine of pi over 6 is square root of 3 divided by 2, well, this is not that difficult. So the descent direction is really minus the Hessian inverse times the gradient. So we need the inverse of this matrix. Of course, we have to compute the determinant first. Here it is. And the inverse is 1 over the determinant, right? And then what you have to do is switch these two in places, right? Since they are identical, nothing happens. And then you have to change the signs of these two. And this is what is done over here. And then, of course, it's just a bit of simplification. Here is the inverse of the Hessian, right? And then you can compute the descent direction minus. Here is the inverse of the Hessian, and here we have the gradient. And if you do the calculations, this is here the descent direction, right? And here it says that you have to use a step size equal to 1. So x1, y1 is the initial point, the initial estimate, plus alpha, which is 1 here, times the descent direction. And if you do the calculations, this is what you obtain. Again, we can check using MATLAB. So this is the function that we have indeed considered. This is the initial point. Here we have indeed one iteration with a step size alpha is equal to 1, and we use the Newton descent direction. By the way, this is software that is available on the web page on the course. So we can run this. Of course, here we only have one iteration. So what you have over here is x0, y0. Here you have x1, y1, and we can have a look at the results. Here we have the descent direction d0 minus square root of 3, 2, right? We can have a look at the first iterate that was produced, and we have produced this value over here, which corresponds. So it looks like we have come up with the correct solution. Well, let's have a look at question 5, right, which is a linear programming problem, right, with a two-phase simplex method, right? So this means that you'll have first an artificial problem. So the first thing that you have to do is to bring this linear programming problem into a standard format, right, to bring it in a standard problem. So first thing that we have to do is transform maximization in minimization. That's quite easy. Maximization of f of x is minimization of minus f of x, and this is what we have done over here. In a standard problem we expect equalities over here, right, and we have inequalities. In this equation here we have an inequality smaller or equal, and so we can bring this into an equality by using a slack variable x4 that is of course positive or 0, right? And in these two cases here we have an inequality larger or equal, so we'll have to work with a surplus variable, here a surplus variable x5 and x6, and again they are assumed to be positive or 0. So now we have our standard problem, but the problem we're facing is that it's difficult to find a basic feasible solution, and this is why we'll solve an artificial problem first. This is really stage 1. What we have done here is take this problem here and add it two additional artificial variables x7 and x8, and we'll use as a cost function x7 and x8. And if everything goes well, we should be able to solve this problem. At the end we'll have x7 and x8 both equal to 0, and we'll also have a basic feasible solution of our initial problem that we have here in the standard problem. So what we have to do now is to write this artificial problem in a tableau form. This is what is done over here, right? You can see that, as I said before, it's quite easy here to obtain a basic feasible solution. It's simply x4 is equal to 6, x7 is equal to 4, and x8 is equal to 7. So the basic variables are x4, x7, and x8, right? And of course the cost function that we have used is x7 plus x8. So before we start, we have to make sure, and this is always what we do when we do pivoting, right, that we have zeros underneath the pivots. This is the case over here, but it's not the case over here. So we have to create zeros in these areas over here, and so what we have to do is perform two basic row operations to create zeros over here, and here are these elementary row operations that we should perform. So in the meantime we have done these two elementary row operations. We have found here a new row below, and we can cross out the old row. So what you see here in this new row are the reduced costs, and we have seen in the course that in order to select the variable that is going to join the base, you have to take the lowest reduced cost, and clearly this is here -5, right? So we know now that x1 is going to join the bases. So what we need to do is to compute this column here, and in this column we have really an element of this column divided by the corresponding element. Remember this is the variable that is going to join the base. So here it's 6 over 1, 4 over 2, and 7 over 3, and you have to pick the smallest one that is positive. So clearly here it's 2, and we know now that the new pivot will be 2. So we knew that x1 is going to join the base, and we have to go and have a look. Here x7 is going to leave the base. So since we have now our new pivot, we have to perform row operations to create zeros above and below the pivots, right? So we have here these three elementary row operations, and also will work with a pivot of 1, so we'll have to multiply this second line here by a half. Remember that to obtain the multiplier over here, if you work with this convention with a minus sign over here, well, you have to take the element to eliminate divided by the pivot. So here 1 over 2, here 3 over 2, and here minus 5 over 2. So once we have performed the row operations that are over here, you end up with the following tableau. Right, and here again we have the reduced costs. The most negative one is this one over here, so we know that x2 is going to join the bases. We have to compute this column over here, and this column, well, you take the elements of this column here and you divide by the corresponding elements of the second column. The second column here corresponds to the variable that is going to join, right? 4 divided by 3 over 2, 8/3, 2 divided by minus 1 over 2, minus 4, and 1 divided by 7 over 2, 2/7. So you have to take the element that is positive and smallest, right? So this corresponds to this element here. We know now that the new pivot will be this one here. So this will no longer be the pivot, so x8 will leave the base and will end the first stage, because both artificial variables will have left the basis, right? So in order to produce zeros above and below the new pivot, here are the elementary row operations that you have to perform, and you have of course to multiply this row over here by the inverse of the pivot. Once we perform these row operations, we obtain the final tableau of stage 1 with the basic variables x1, x2, and x4 with associated pivots, right? And we can see that everything is okay because we recover the original cost x7 plus x8, and you see that the sum of x7 plus x8 is 0. So what we have done here is obtain a basic feasible solution for our original standard problem. So what we can do now is cross out columns x7 and x8, remove this cost here, recopy the tableau, and this is what you obtain. We have added the cost here of our original standard problem, right? So now we have a tableau, but just as before over here, we have to ensure that above and below the pivots we have zeros. This is the case over here, but clearly not over here. We have to produce zeros over here, and this can be done using the following elementary row operations. Here we have produced the new row. We have crossed out the old one, and we have obtained it by performing these two elementary row operations, right? So what you have here are the reduced costs. We picked the most negative one, and this corresponds to the variable that is going to enter the base. It will be x3. To know which variable is going to leave the base, we compute this column over here. So it's the elements of column B divided by the corresponding elements of column 3, right? So here we have the elements. We take the smallest one that is positive, and this corresponds to this element over here. So we know that this is the new pivot. This was the old one, so x4 is going to leave the base, right? So we have to produce zeros here below the pivot, right? And this is done by these three elementary row operations, and we have to create a line here with a pivot 1. So we have to multiply this line here by the inverse of the pivot. So this is the new tableau after having performed the following elementary row operations. Again, we have a look at the reduced cost over here. This is the most negative one. So x6 is going to enter the base. To know which variable is going to leave, we compute this column. So we have elements from the column B divided by the corresponding elements of column 6, right? So 25 over 3 and so forth. And this one is obviously the smallest one. So here we have our new pivot. X6 is going to enter the base. This is the old pivot, so x3 is going to leave the base, right? So we need to produce zeros below this new pivot over here, and you do this by performing the following row operations. And then of course we want a row with a pivot that is 1, so we have to multiply this row here by the inverse of the pivot. So by now we know the drill. Here is the new tableau, right, having performed the following elementary operations. Again, we have the reduced cost. There is still one that is negative, so it can still reduce the costs. X5 is going to enter the base, right? So we compute this column, the elements of column B divided by the corresponding elements of column 5 over here. The two first are negative, so we cannot take it. So the smallest one that is positive is obviously this one. So this is our new pivot, right? The old pivot is over here, so it will be replaced by this pivot over here. So we know now that x2 is going to leave the base. We have to create zeros above and below the pivot, and you can do this using the following elementary row operations. And we have to create a row here with an element that is 1 at the pivot, so we multiply the line by 3. So we arrive at the end of the problem. We have our final tableau here, having performed the following row operations. We can see here that all the reduced costs are positive, which means that we are at the end of stage 2. We have 3 basic variables, right? X1, which is an original variable, and the other 2 basic variables are the, well, here are the surplus variables, right? So we can read the solution. In terms of the original variables, we see that x1, which is basic, can be read over here. It's 6, right? The other original variables are non-basic, so they are 0, right? So if you plug this into the cost, we see that the cost is indeed 18, and this matches with what we see over here. We see that x4, which is the slack variable, is non-basic, so it's 0. And indeed, if you plug in the solution in here, you'll have 6 on one side and 6 on the other side. So indeed, there is no slack. The first surplus variable, x5, is 8. Indeed, if you plug in the solution over here, you'll have 12 and here 4. So you have a surplus of 8, and this is correct as well. If you plug in the solution in the last inequality, well, you'll have 3 times 6, which is 18, and you have a surplus of 11, and this is also correct. And this is the end of, well, question 5. What we can do now is use MATLAB to check the result. We can use the function linprog, but you have to write the problem in such a way. So we have to use a minimization problem. This is something that we have done as well. And we can take the original problem with inequalities, but all inequalities should be smaller or equal. This means that in the second and third equation, we'll have to multiply by -1, right? And we have only lower bounds, which are 0, right? So if we have a look at our problem, we had that the second and third equation were larger or equal. So if we multiply by -1, it will be okay, right? If we have a look at this MATLAB function, here we have our minimization problem. Here we have our A matrix. See that we have in the last two equations multiplied by -1, so the coefficients have changed sign, and this is the case also in the b term, right? And here are the lower bounds, and if you use this lin-proc MATLAB function, you end up with a result that is exactly what we have found. Well, let us now have a look at question 6, which is also the last question, and which is a question which is traditionally about the Lagrange multiplier method. So we're given a pyramid, and it's bounded by a plane that is given over here, right, where A, B, and C are strictly positive. So this is one plane of the pyramid, and the other three planes are the three coordinate planes, right? So you need to use the Lagrange multiplier method to find the largest possible volume of this pyramid, and knowing that this pyramid, or that this plane here, has to go through the point with coordinates 1, 2, 3. So you will have, of course, to look for variables A, B, C that satisfy this condition over here, right? And to help you, note that the volume of a pyramid is equal to 1/3 of the area of the base times the corresponding height. So what you should do is try to do this by yourself if you're preparing your exam, and the first thing that you should do is probably draw the pyramid. Well, as you can see, the solution is quite straightforward as soon as you have made a drawing of the pyramid, right? So the easiest thing to do is to draw the three coordinate axes, x, y, and z, and then to look at the intersection of each axis with the plane, right? So for instance, the x-axis, on the x-axis, well, all coordinates are 0 except the first one, and if you plug this in, right, you see that x has to be equal to a. You can do something similar for the y-axis and the z-axis. So we have now 3 points, 1 point per axis, and you can draw, well, this plane, right? And then you can see that the pyramid is formed by this plane, right, and the three coordinate planes, right? This plane over here, this plane over here, and this plane over here. And you can clearly see the pyramid, right? The volume of the pyramid, well, you can take a basis. For instance, I've taken this basis over here, and it's quite easy to compute its area, right? Because you have a right angle here, so the surface of this triangle is simply A times B divided by 2. The height here is C, and if you apply the formula, you can obtain the volume quite easily. So we have one constraint. The point 1, 2, 3 has to be a part of the plane, right? So if you plug this in to the equation of the plane, the equation has to be met. If you do this, this is the constraint that you obtain. So here we have a function that we want to maximize, right? And here we have the constraint, so we can write the Lagrange function, which is a function of the original three parameters, and we have a Lagrange parameters that is added. This is, well, what you have to pay, one additional parameter, but the advantage, of course, is that now your problem is unconstrained, right? As usual, if you have to optimize a function, you compute the gradient, the partial derivatives with respect to all parameters, a, b, c, and lambda, and if you do this, this is quite easy, this is what you obtain, right? By looking at equations 1, 2, and 3, you can isolate lambda, and here you've got it, right? And then if you take these equations here and you simplify by a, b, c, which is in common in each equation here, you know that they are positive, right? You end up with this equation, which you can further simplify to this equation over here. So you know that B is 2 times A and C is 3 times A. So you can use this and plug it in equation 4, and this is what you obtain, right? You can isolate A and you find that A is equal to 3. If you plug it in to these equations, you can very easily see that B is equal to 6 and C is equal to 9. And this concludes this video that looks at the solution of the exercise questions of the exam of June 2024.